So we have looked at how the APB protocol works, and some of you might have also looked at how to do a basic APB slave design. And this session we are going to focus on the APB protocol from the verification point of view. And this session expects a prerequisite that you have understood SystemVerilog and how the UVM works. And then depending on how much familiarity you have, and then how much you're comfortable with those two, it would decide how well you will be able to absorb this particular session, because it's a practical session. It shows you the code example, so you need to have some level of understanding and comfort in order to absorb it. So some cases you might have to go through it like maybe twice to get the points. If your UVM concepts are not very clear, you might want to revisit UVM concepts that you are not finding a clarity, and then come back to this session to understand. So that might be required for some of you. So let's jump into the agenda for this session. So for this session, our agenda is we want to build the entire test bench components for verifying the APB, and which involves, we'll start off with very basic. We want to connect a APB agent, so we need a APB SystemVerilog interface. Then we will connect the APB agent to DUT, and then we'll create a bunch of sequence items and sequences that we can initiate. Then we'll initiate some reads and writes through the tests, and then we'll look into how to create a master agent. Then like how do we build the master driver, how do we build the master monitor, and then how do we build a functional coverage model within the context of agent as well as the external. We'll look at it. And then how do we create APB assertions. So APB assertions, like if you want to build the concurrent assertions, how do we do that? So we will cover all these aspects, and as we discussed, it requires you to have good familiarity with both the UVM as well as the SystemVerilog to absorb this session clearly. So the theoretical part about UVM will be very brief, and this is just to build the context. So the central idea of building verification components around APB is the APB verification IP, or the APB agent. So for the APB, we are building the master agent because we have built the slave design. We are building the APB master agent. So we'll just quickly define the agent. And agent is primarily what it does is it connects to DUT using the virtual interface, and then there are a bunch of sequence that it provides which enable the stimulus generation, and when you run the sequence, it creates the sequence items. The sequences are initiated from your tests, and then the sequences that get initiated on the sequencer gets driven to your driver through the sequence item port, and then the driver drives them the sequence item that it has received to the virtual interface, which eventually goes to stimulate your design. And then any of the activities that are taking place on the interface is monitored by the monitor that is present within the agent, which also uses the virtual interface. And whatever the monitor transaction that it is able to detect, it sends it out through an analysis port. Analysis port provides you an ability to do 0 to many connections, and then to those analysis ports, the coverage subscribers or the scoreboard based subscribers can get hooked up and use those transactions and process them. So this is the basic idea of the agent, and we will look at one more like overall UVM test bench picture, and then thereon we'll jump into the code level details. So this is the overall diagram of the UVM test bench, a very simple UVM test bench. So you have a test at the top, then you have the environment. Within the environment there can be multiple agents that can be present, and then our focus is on building one of these agents, and those agents contain the config, and typically the test has the ability to configure the environment both structurally as well as functionally. Structurally meaning the number of agents it wants to create, and the configuration, the structural configuration in terms of the parameterizations for the agents, and then the functional configuration where the behavior of the particular agent is controlled during the runtime. So those two types of configuration information. So the test configures it to the environment, and environment configures it to the individual agent configs. And then there are a bunch of sequences which the test will initiate, monitor. Then you have the analysis port, multiple, like there can be a coverage subscriber, there can be a scoreboards that are getting connected, and then connection to the DUT happens through a set of the virtual interfaces, and then the connection between your sequencer and driver happens through the your sequence item port and its implementation. Then I have not shown over here the concept of RAL. So if you have the register blocks within the DUT, then the RAL block will come into play, and that RAL block can be mapped to one of your agents through the adapter to initiate the transactions on the bus. So we will briefly be using that concept as well as a part of this session. So let's start off with defining the SystemVerilog interface for the APB. So we are defining a interface APB, and then we are taking the P clock and P reset. And if you remember, when we had discussed about the APB signals, the P clock and P reset N is something that is coming from a system, overall system that is getting implemented. So the APB interface is receiving them as inputs, and then the rest of the signals are defined over here. And you can actually implement any properties or coverage within this interface as well, or you can create a separate interface to implement that so that this particular interface definition remains clean. So in this current example, we are showing both the ways. So as a part of this session, what you will see is the different ways to implement the same things. Okay, a few variations that are possible you will be able to see. And again, as we discussed even during the design session, what you need to keep in mind is the goal is not that this is the ideal or the perfect solution. This is show you one of the flavors and show you few variations that completes your understanding. We will take a top-down approach. So we will start off from the UART test bench. We are importing the UVM packages, and we are importing all the test packages, and there are many details that we really don't worry about it too much. Our focus is from the point of view of how the APB gets used. So we had declared an APB interface in the previous slide. So we create a instance of that particular APB interface, and we pass this global P clock and P reset N as a parameters. Then if you remember, we had looked at as a part of design series, our top for the design was a UART block, within which we had APB slave logic implemented in that register file module. So this is the top module. So we are instancing our DUT, and then the instance DUT, we are connecting the all the the APB related signals are all connected over here, and these signals, if you look at it, they are getting connected to the corresponding signals within the APB interface. So we have instanced the APB interface, we have instanced the DUT, and then we have connected the corresponding DUT signals to the corresponding APB interface signal. So that is the first step that we have done. And then now this interface needs to be passed as a virtual interface to the class-based word. This is the static word. So from the static word, we have to pass this interface to the class-based UVM word, and that we generally do it in the UVM recommendation is we do it through the config DB. So we put this initial begin end. As you know, the run test is a entry point for the UVM. So through the config DB, we set up that in the like a virtual APB interface. We set this, and then our default this at the test bench test top, whatever the default test is running, that will become the test top. The name is the APB interface. Since there is no class hierarchy, we are passing it with a null, and then we are passing this APB interface instance that we had created at the top. So this part of the code, this initial beginning, is the part of this module URTB. So this is continuation. Okay, So that's why I'm showing that these two belong to this module itself. So we are setting it up. There are a bunch of other interfaces that are being passed. Don't worry about it. Next is we also have an APB protocol monitor. This is something that might confuse you at this point. We have been talking about agent. The agent will come in the environment. Then a question might come in your mind of why do we have again an external monitor? So we have external monitor because we want to put the concurrent assertions. Concurrent assertions cannot be put in the class based word, correct? So we need to put them in a static word. So there is an external APB protocol monitor implemented as an interface. So we create another interface construct and we connect this interface to the APB interface that we have instanced to connect between the test bench and the DUT, right? So through this interface we are connecting the DUT and test bench, and to this interface we are also attaching another interface which acts as a protocol monitor, and it has exactly the same signals, and we are connecting our APB interface that we have hooked up to this monitor. This monitor will have all of these signals as input. Okay, it will not have any one of them, it will not drive anything, it will just monitor them and implement some concurrent assertion. We will look at it in much deeper towards the end of the session when we start talking about the monitor. But for now, we have the top level test bench, we have our APB interface instanced, we have instanced our DUT, and we have connected this APB interface that we had instanced to our DUT, and then we are setting up it as a virtual interface type and passing it to the desktop, whatever the APB interface that we have configured. Now next step is inside the test will extract this particular interface and then put it in the APB config, put the APB config in the overall environment config and pass it down to the environment, and environment will take it and distribute it to our APB agent. And our ultimate goal is that APB agent should receive this virtual interface and then use it for driving and monitoring. So that is the overall big picture. So now let's look at how the test the extracts this information and sets it up for the environment. So how does that connection of the interface takes place in the next few slides. Okay, so after we have connected our DUT and the test bench, the first thing, as we saw in the block diagram of the UVM test bench, the test is the top, right? So we'll start off from the test and then drill down further. So let's start with a simple test. We have a UART test. It extends the UART test base. So it's generally a good idea that all the common things must be put in the base test. So that has been done. So it extends. We'll look into what this base test does. Hold that thought over there. And then it has these because the test hierarchy is extended from the component, it is aware of phase aware. So basically it will implement your run phase. Most of the key things will happen in its run phase. So in the run phase, what we are doing is we are creating one basic register virtual sequence. Okay, so we are creating an instance of that, and then in the test we are raising the objection so that the test holds the control till the test completes. The test holds the control of UVM being able to finish the test execution till it's really done, and then we start off this particular virtual sequence. Okay, so we init it and then we start it off. Okay, so once we start this particular virtual sequence, it goes to this basic reg v sequence that we had created, and the body, once we call the start, we are passing the null because it's a virtual sequence, and then the body of this particular virtual sequence starts execution. In this body we are creating one more sequence called quick register access sequence. So we are creating this using the factory, and then we are starting it on APB sequencer. Now we don't know how this APB handle came over here. Hold that thought. The second thing we are holding our thought, one is what is happening in the base test and how did this APB sequencer handle made its way into this particular virtual sequence. So we don't know that. Hold that thought over there. But anyway, so it starts on this APB sequencer, and then this particular quick reg access sequence will be started, and the body of this particular sequence will be executed. And as a part of the body of this particular sequence, it starts initiating the reads to the set of registers. So some of these registers names, LCR for example, we had looked at how we wrote it right in the design context. So all these registers are read through the RAL module. Okay, so when you read it through the RAL module, what happens is you would have assigned an adapter corresponding to this particular RAL model. On that particular so that particular adapter creates the sequence items which get executed and then they reach the driver. So that is the big picture. So we are initiating the read, so the control will go to the adapter. So how does the adapter behave? Let's look at it in the next slide. This is our register adapter. So we have created this reg2 APB adapter. We will set this up. So we'll go to environment. So we still have that base test open. We still have that virtual sequencer handle open. Hold those thoughts. We will be assigning this reg2 APB adapter in the environment. Okay, hold that. That's the third point we will look at it. So in the adapter, what happens is that whenever the read write is initiated from the RAL, the way we looked at it over there, right, like the RAL module .lcr .read or .write, when we initiate that, the reg2 bus function gets called, and as a part of this, what we are doing is we are creating an APB sequence item. We have not looked at APB sequence item. We will look at it. So we have created an APB sequence item, and then the APB sequence item has these fields: write enable, address, and data. Those are the three key fields from the higher level abstraction point of view. Note that when we create the sequence item, we don't define all the signals. Okay, the signal level activity is responsibility of the driver and monitor. It's not the responsibility of the higher level test as to how to manage, let's say, a ready or how to drive some address bus. Those are all the responsibilities of your driver and monitor. Ideally, you should not be declaring any signals which is not visible from a software point of view. So your test, you think of it like a software. So from our test point of view, what are we ultimately planning to do? We are planning to just do the read write. So when we do the read write, what we need to tell, what is the address, whether it is a read or write. If it is a write, we'll send the data. If it is a read, we'll receive the data. So that is why we have only these three core fields which are visible to software, and we are creating that as a sequence item, and then based on whether it is a read or write, appropriately those particular properties of the sequence item are set up, and that is returned. Now that sequence item will execute on the sequencer on which that particular virtual sequence is running, and then that particular access, that sequence item gets transferred to the driver for the execution on the signal level interface. And when that particular sequence completes, then you will be initiating bus to reg function call from the adapter. These two are built-in functions, and this guy will actually now transfer the data that is being read. So in this case, what we are doing is there are multiple ways to send data from your driver to the sequence. In this case, we are using the property that is present within the sequence to send the data back. So we are assigning whatever the data that has come from the completed sequence item, we are sending it back. So what we now need to look at is, so we need to also look at how this reg2 APB adapter gets initialized, and we'll look more deeper into the sequence item in the next few slides. So let's now pop some of those items that we have pushed on the stack, where we said we will understand. So first let's address the base test from which we had extended our UART test, which we are running currently. So this is the class UART base test, and it's extending from the UVM test. UVM test is the base class library, so there's no more hierarchy at the user level at this point, and it's registering for the factory, and then it is creating a UVM, the APB agent config, and then we'll look at its build phase. So as a part of build phase, what it does is it creates the APB config, and in that particular APB config, what it is doing is it's trying to extract the virtual APB interface, right? So if you remember at the test bench top, we had set this into the config database for the UVM test top, and whatever the test running will be the UVM test top, and now this particular test is extracting the APB interface into this APB agent config. So in the APB agent config we have the handle for the APB interface, and this one is extracting that APB interface into the agent config. Okay, and then additionally what it is doing is whatever this APB config that it has created, it's making it a part of environment config. So there is an environment config, then the APB agent config, we are assigning this particular instance. So now we have created an overall environment config, and this environment config ultimately gets passed down through the config DB again, and the config DB and the environment picks it up from the base test. We created the overall environment config to control how the environment gets created and gets configured, and that is picked up from the environment and it builds according to whatever that is the requirement of the test. Okay, apart from that, we are setting up, important point for us is we are setting up the address decoding for this particular slave. So we are setting up the start address equal to 0, and the range that we wanted to set up, we are setting it up to hex 30. That is more than enough for this particular APB slave. It's more addresses than what it really requires, so some of them we can use it for the error injection. That is the idea over here. And when we look at the agent further, you will see that the agent will be using this particular the address range that we have configured for detecting the P cell. However, in this current case we still have only one slave, but in case of multiple slaves we can set up multiple address ranges. So you can see that it is an array, it's not a single element, right? So you can set up 16 of these, and that will decide which P cell value is going to get asserted. And then we come to this, there is one more task called init v sequence, which is a part of this base test which gets called. And in this init v sequence, what we do is we set up the APB sequencer handle. Okay, so in the v sequence.apb, then we set up this particular m sequencer from the APB agent, and this is what we were using it in the virtual sequence that we were running. Okay, so this resolves those two items, and we will continue further to resolve the queries that we have raised in the previous slides. Continuing our journey top to down, we started off from a UART test that was extending a base test, and that was starting a virtual sequence that was initiating some read writes, and we said that those read writes were initiated through the RAL, and then the adapter would get initiated that whenever we do the access to the register, the RAL block, right? So the reg to bus will get initiated within the adapter whenever we did the read and writes to the RAL module. So, and then we looked at the base test that we were extending, and in the base test we had created the APB agent config, and we configured the address range, and we configured the virtual interface that we had set in the TB top into the corresponding agent config. We have configured that, and then the APB agent config, we put it into the environment config. So similarly, multiple agent configs will be put in the environment config, and the base test will set that environment config into the config DB, which then the environment will take it out and distribute it to the corresponding agents. And our interest is again the APB agent. So if we come back to the UART environment, so it's extending a UVM component. It contains all the phases, and then we will look at, so we have the UART environment config, which is the overall config that we have, and then we also have the APB agent, right, that we are declaring over here, to which we want to pass the corresponding APB agent config, and we create an instance of the register adapter that we had already seen, and that adapter, if you look at in the connect phase, we are assigning it to the reg predictor, adapter, right? So this is the RAL model. Whatever the RAL model, we are setting up the sequencer to be the sequencer of APB, and then we are setting up the adapter for that as a reg adapter that we had already seen, which contains the function that whenever bus to reg gets invoked, it will return an APB sequence item which can be run on this particular M sequencer, right? So M sequencer from the APB agent. Okay, so we need to look at the APB sequence item. We will do that first. So we have now closed on how the RAL adapter gets set up in the environments connect phase. We will look at how the agent config gets set up, because within that config we have the virtual interface which can be used by the driver and the monitor present within the agent. Okay, so we are in the build phase of the environment. So in the build phase of the environment, what we are trying to do is we are trying to get this UART environment config. This is the overall config that was set in by the base test. Okay, so we get that in, and then what we do is we extract the we create the APB agent over here, and then in the config DB we set up the APB agent config that we want to go to this AMPB agent. So this AMPB agent is the instance name from this environment.AMPB agent, right? That is the hierarchy through which it will extract this APB agent config parameter value or the string value, this particular key, and the value for that particular key in the config DB would be our M config, which is the overall environment config, and from that we are passing the M APB agent config. So once we pass this, this particular agent config contains the virtual interface and the address decode range for every slave. So currently we have initialized it for only one slave, but we can initialize it for the multiple slaves. Okay, so this way now we have passed the agent config, and we will look at how the agent config is able to, how the agent is able to, and we have created the agent, right? So now we will look at how the agent will be able to extract this particular config and use the virtual interface and the address decode that we have set up. Before we proceed to that, let's look at one last detail from the environment point of view. So we have built the agent, and from this agent, if you look at it, the analysis port is present. So when we look into the agent's detail, we will be able to see this analysis port. So this analysis port is connected to this TX scoreboard and the RX scoreboard, and then even this RAL predictor is able to connect to this analysis port. So multiple subscribers are getting hooked up to this analysis port. So at this point, the agent has been created, and then the agent's analysis port is connected to both the scoreboard as well as the coverage subscribers. Of course, we don't have coverage subscriber here. We have the coverage subscriber within the agent. So we will look at it in the next few slides. But at this point, next step for us is how does the agent will be able to extract that particular agent config. So that is a next step we will look for. Okay, before we jump into the agent, so let's quickly do three things. First is we will do the sequence item definition, sequence, and then the config. Okay, so let's look at these three, and then we'll jump deeper into the agent. So we have APB sequence item over here, which extends from the UVM sequence item, and it's registering to factory using the object utils. And as we noted, we are not declaring any signals. We are declaring only the properties in a way that will be visible to software or the test would like to control. So address data write enable, as we know very clearly, mapping to what the software wants. Delay is an extra parameter that if you want to insert delays between the APB sequence item within the driver, then you can control it over here. Then you have one error injection state property that you can use it for controlling. You can define the constraints over here. We are defining the addresses to be the D-word aligned. If you remember, while connecting, we have anyway ignored the lower two bits. So it's a dword aligned addresses, and then we are setting up some default constraints for the delay. And then every sequence item, as you might have seen, it needs to implement these standard methods of do copy, do compare, then convert to string, do print, do record, which gets called when the corresponding function like this particular sequence item dot copy dot compare, when they get called, these particular sequence item functions will get invoked. The corresponding do underscore copies will get invoked. So we have a simple constructor, just has the name, no parent, because it's object type, not a component type. Then we have the do copy implementation. We are passing the RHS argument over here. Then we will see that we are doing the casting check because it's coming via the object class handle. A derived class object is coming via a base class handle. So we are declaring the expected data type and casting it and check whether the the type casting passes, and if that passes, we first initiate the base class copy, and then we come to copying the elements that we have defined over here. Okay, so we do that. This is how the do copy works for the APB sequence item. Let's look at few more methods. So we have the do compare, and what we are doing over here is the process is similar. Then we do the casting check. Then we have the comparer, which is the policy checker for the UVM. We do the super dot do compare, and then we are not using that comparer at this point. We are just checking field by field. We don't need to compare the delay, right? So we need to compare only the fields that matter from the overall APB operation point of view. This is mainly going to get used in the scoreboard. And then you have the convert to string. You use the S format with the corresponding format identifiers that will create this particular string, and then you return that string. And then you have the do print, where you use this UVM printer and then assign that particular string with the convert to string call, which will print this particular sequence item for the debug wherever we require. Is going to print it in the single line in this particular format, which is very helpful for grepping it out from the log files. And then you have the do record, where the transactions can be recorded in some file or database for the implementation of debug infrastructure. So we are specifying all the fields using this tick UVM record field macro. So this provides the how you can implement your APB sequence item and its standard UVM methods. So this is the APB sequence, so it extends the UVM sequence. We are parameterizing with the APB sequence item, and as we know that this particular sequence is using the same sequence item for sending both the request as well as response. In fact, within this sequence item we have a data property which gets used for sending back the response. So we are using only one. The same request type will be used for the response type as well. But we are not sending anyway the response. We are using the same sequence item for copying the data that is being read. Register to factory using the object utils. Then the constructor, we are just passing the name, main important part being body. We create one APB sequence item request. Then we create it using the factory, and then we call the standard handshake sequence with the sequencer using the start item. So when we say start item, it will request to the sequencer, and the sequencer will arbitrate and then wait for the driver to request for an item, and then when that happens, the start item will unblock, and then this late randomization of the request takes place so that it can be randomized with the correct state or the current state of the system. And then after randomizing, it checks whether, because randomization can fail due to inconsistent constraints, so it checks whether the randomization has succeeded, and then it calls the finish item request, in which case now the actual randomized APB sequence item now gets passed to the driver, and the driver will be able to execute this particular sequence item, and if it is a read, it will copy the data back to the particular sequence item, and it will call item done, and then this finish item gets unblocked, and that item done and the finish item over here, this also invokes the adapter, and the adapter copies the data and returns it back to the RAL model to the test where we had initiated the read to the particular register. So this is the way the overall things get stitched. So we have looked at the sequence, and we have looked at the corresponding sequence item and how that gets implemented. Now let's look at the configuration, and after that we'll jump into the more details of the agent. So we have the APB agent config, which extends the UVM object, and then it's doing the object-based registration to the factory. And internally, if you remember, we were setting up this virtual APB interface within the APB agent config, and then we have whether it's a active or a passive agent that we can set it up. And if it is only a passive agent, then only the monitor gets instance. If it is an active agent, then both the driver as well gets instanced. And then we have these additional configuration parameters where we are saying the number of select lines is equal to only 1, and we are saying the APB index is equal to 0, which is the P cell for which we intend to connect our slave. And then we have only one start address and range defined over here, but we are going to initialize only one, but you can see that we have 16 of them that we can utilize for connecting the different number of slaves from the APB config, and then at that point of time you can set up the number of select lines also appropriately, which gets used in the agent. So we look at how this information for address decoding that we have set up gets used in the agent. So how this is used for figuring out the P cell line that needs to be driven, that will come to know in the driver. Okay, now that we have seen the details of the sequence item, APB sequence item, a simple sequence, and we have also seen how the APB config, what information does the APB config contains. So we have all the basic building blocks. Now we'll jump into the actual agent. So our APB agent extends UVM component, does the factory registration for the component utils, and the main detail is, yeah, it's declaring the APB agent config, and then it is declaring an analysis port. So this analysis port connection is something we saw at the environment level that gets connected to multiple scoreboards as well as to the RAL predictor. And we are creating the instance of monitor, sequencer, driver, and then we are also creating an instance of the coverage monitor. So these are the 4 instances. Typically you have monitor, sequencer, and driver. There's additionally the coverage monitor is also made a part of the same agent. So we have looked at the APB agent declaration. Now let's look one level deeper into how the implementation happens. So first let's look at the build and the connect phase. So as this is the build phase task. So in the build phase task, the first step that we are doing is from the config DB, we are extracting the APB agent config. Okay, because that's where the virtual interface is located, and we are saying this because this will be that whatever our testbench desktop.environment your M agent, AMPBA agent, right? So this is the instance name. So we are not passing anything for the instance name, so that path will match, and we will be able to extract the APB agent config key from that particular config DB key value pair, and the value will be extracted in the M config. And then we are creating the monitor using the factory, and we are checking if it is an active. If it is active, we are creating the driver sequencer instances, and we also have the configuration. So this is a good idea to put the check that whether the functional coverage needs to be enabled. If it is enabled, then only we instance the functional coverage monitor over here, and then we create the analysis port that we had declared, which will get connected to multiple subscribers and the scoreboards eventually. And but the key thing is we got this M config. Now let's jump into the connect phase. So in the connect phase, if you look at it, we say mmonitor.apb. So we will look at it. So this APB handle is a virtual interface handle that is declared within the monitor. So we are now and in the mconfig.apb. So in the agent config, we had already initialized the interface handle for the APB, right? So that goes to the monitor now. Okay, and then the monitor APB index is copied from the mconfig APB index that we had specified, and then the monitor analysis port is connected to the analysis port that is present at the agent level. So this is a port-to-port, agent port-to-port connection, and then further you can give the implementation, right? So when we finally connect to the export and then provide the implementation. So this is just a port-to-port connection that is taking place, and we have again, it also checks if it is active, then the driver sequence item port gets connected to the sequencer's sequence item export. Okay, so this is where we connect the sequencer and the driver, and to the driver also contains an internally virtual interface for the APB, and that is initialized with the mconfig.apb. Okay, so this way we connected it at the test bench top, and then through the base test we put it inside that APB config. That APB config we had put it in the environment config. Environment config was put in the config database, and when the FIFO the UART environment build happened, it took out that overall UART environment config from the config database that was set up from the base test, and from that it took out the APB config and then set it for the APB agent instance, and then in the APB agent instance, the APB agent extracted the APB agent config. Within that, it contained the virtual interface for the APB. That virtual interface for the APB now has been passed to both the driver as well as to the monitor. Right, so now we are set. Okay, so now we can go into the monitors and drivers and see how they are able to use this virtual interface to implement their functionality, and all the analysis port we have connected. So now let's go further deeper into the drivers and the monitors and the the coverage monitor and how they are implementing their functionality. Let's look into it. This is just a boiler code for the sequencer. There are now new macros available to generate this code. Nothing very specific to functionality. You just say APB sequencer extends UVM sequencer parameterized by APB sequence item, do the factory registration, then just have the constructor and the constructor implemented containing name and the parent, because it's a UVM component hierarchy, and this gets used within the APB agent. Okay, so we have looked at the high level agent and how everything gets instanced and how the virtual interface gets passed on to the monitor and driver. We will look into how monitor and driver use them to implement their functionality. So let's start with the driver. So we have class APB driver extends UVM driver parameterized by the APB sequence item for both the request and response, doing the factory registration, and the most important, we have the virtual APB IF APB, and if you remember, this was set to the APB interface that we had connected at the test bench top in the agent connect phase, and we have the agent config as well, and then we have the standard UVM methods. I think the most important for us to look at would be the run phase. So let's jump into that. So this is going to be a bit involved slide, and this is the core part of it, so pay attention over here. So what we are looking at over here is we are looking at the run phase of our APB driver, and we have declared these bunch of requests and the responses, and then we have the port index, and since we have the access to the virtual interface, we are just initializing it over here, waiting for the reset to be released, and this is all the basic stuff. And then we have the forever loop where the main driving functionality gets implemented. We initialize the signals with a non-blocking any virtual interface. You have to drive it with the non-blocking to avoid the race possibilities. And then on this line number 64, we are doing sequence item port get next item. This is what initiates your handshake between like a sequencer and a driver. That handshake gets initiated at this point of time. The driver is telling it is ready to take in a sequence item, and the sequencer will now coordinate between the sequence and the driver to send that particular request, and then the request becomes available. So once the finish item hits over there in the sequence, the randomized request becomes available into the driver. And now first thing that driver does is, if you remember, one of the properties that we had in the APB sequence item was delay. Then those many number of delays are implemented in terms of peak clock, and then we have the main functionality to drive the APB interface. And after driving the transaction to the APB interface, we say sequence item port dot item done, which unblocks the finish item at the sequence level, and the overall sequence complete. So this is the overall functionality. Now let's jump into how we drive the APB interface. And now remember that we are implementing a master interface, so we should be able to see this state machine again into the action, the 3-state state machine. So first step, what we need to do is we need to figure out that which P cell value that we need to drive. Current one, although we have initialized it for the one slave, but as we know, we can initialize up to 16 slaves. So how does this work? So we need to understand that a bit over here. So we have a function called select lookup. So it's a part of your driver functionality. And here what it does is, if you remember, we had initialize those number of select lines. So we had initialized it to 1. Okay, so that we can initialize to any number through the config. And then what it will do is it will check if address, that the current address that we are processing, which is what we have passed over here, request.address, is greater than the address that we have configured. So here it will be running from I0 to less than the select line. So for us it will be only 0th, but it can be any, right? So for different indexes we could have mapped different address ranges. So it checks that whether the current address belongs to the range. So it is greater than or equal to the start address, and less than or equal to start address plus the range that we had configured in the APB config, right? So whether it matches that particular range. So if it matches that range, then it returns that particular index. So that will be the P cell value that we are going to drive. So the corresponding P cell index corresponding to that address decode range. So we can have multiple decode ranges. We matched it up, and the corresponding index is now returned. And that P cell index, if it is greater than 0, if none of them matches, of course it's returning -1, which is an error condition. So if it is greater than 0, then what we do is we say APB dot P cell signal, which is again a 16-bit vector. In our case, we are saying P cell index equal to 1. Okay, so this is a phase where we are entering the setup phase. Okay, and in the setup phase, as we know, we have to drive all the control information. So we are driving the P cell, we are assigning the address, and then we are assigning the data that we had received, and then whatever the write information that we have received, that also. So all the control signals are being driven, and the main thing is P cell is being driven. So we are implementing the setup state over here. Next step, after setup, unconditionally we stay in the setup for one clock cycle, then unconditionally transfer to the access stage. So this one clock is what helps us stay in the setup stage for one clock, and then we transition to the access phase. And in the access phase, what we do is first thing we do the P enable. Correct. So that's the first thing that we do. So access phase is a phase wherein we want to access the data. If it is a write, we want to write the data. If it is read, we want to read it. And first step is we have to enable, we have to drive the enable. So apb.p enable non-blocking assignments gets driven, and then we have to wait for slave to say that it is ready. So we say while not APB of P ready, we say at pause edge of clock. So this is the blocking statement over here. So it will keep on waiting till the P ready comes in. So if the P ready is 0, it will remain in the access state, and once the P ready has been asserted, then what we do is if it was a read, then we just copy the request.data with the data from the PR data bus. Okay, we copy that information, and at this point the overall driving is completed. Okay, so if the P cell index was negative, then we are issuing a error message over here, tick a UVM error, that this particular access is out of the address range. Okay, and then we are setting the request.error. If you remember, we had defined a property, state property, which is non-random type, that we are setting the request.error equal to 1 over here. So this is how the overall driving functionality works in case of the APB driver. So now that we have looked at how the driver works, we'll now look at the monitor. So we have our class APB monitor, and then it extends UVM component, and then it's doing the factory registration for the UVM component details. The most important point is that it has a virtual APB interface of the, and we are calling it as APB, and this is the virtual interface that gets initialized at the agent top after we got the agent config, which contained the interface that gets initialized to this particular monitor. And then we had initialized even the APB index in the connect phase of the agent. And then if you remember, we had connected this analysis port to port connection we had done at the top of the agent. Then the main thing that we are going to look at over here is the run phase. Apart from that, in the build phase is just the analysis port gets created, whatever the analysis port that we have created, and then since there's no factory override for the TLM ports, it just directly using the new, and it gets constructed over here. Let's look at how the run phase for the monitor gets implemented. So this is the run phase. Now note that we are calling this as within the agent because we have two monitors, right? So one monitor that actually does the protocol checks, and this monitor just monitors the interface, creates the transaction, and distributes it to all the subscribers. It's not doing the protocol check. Protocol check is done by the external monitor that's implemented as an interface, and which is implementing the concurrent assertions. Because this is a class, we cannot do concurrent assertions within the class. So here what we are doing, we are creating one APB sequence item, and then we are creating that particular item, and then we have the monitor, the APB interface functionality. All the monitors and the drivers, they always contain this forever loop, and it's doing all the operations on the passage of the peak clock. Same thing we did it in the driver as well. So at the passage of the peak clock, it checks if the APB ready and the P cell are asserted for the ARB index that has been assigned. Okay, so if this particular has been asserted, then what we do is we take the item address from the P address, APB P address, and we assign it to the item that we have created. Write enable, we assign it, and if it is a write, then the data is copied from the PW data interface. If it is a read, then it is copied from the PR data, and then it does the cloning of this particular item, and the cloned item gets sent over the analysis port. Anyway, so all the subscribers are not expected to modify this transaction. They should just, if they want, they should again copy it, do a deep copy within their own processing, and then if they want to modify or change it or store it for the further reference, they need to do that. So here when we do the ap.write, the corresponding write implementation in all connected analysis port subscribers or the scoreboards get invoked, and they get to see this particular transactions. Again, I am iterating that this is not doing all the checks. Okay, so the checks are done as the part of the external protocol monitor. This is just monitoring the interface, and it is creating the transaction, and the main thing is whether it is a read write, and then what is the data that it is capturing and sending it out to the scoreboard and the subscribers. We have been looking at the various components within the agent. So we have looked at APB agent. So we looked at the monitor, we have looked at the driver, we looked at the sequencer, which was just a boilerplate anyway. And now we will look at the APB coverage monitor. So this is the coverage monitor that is present within the agent. So we have APB coverage monitor, which extends your UVM subscriber, which is going to provide the implementation for the analysis port write, parameterized with your APB sequence item registered to the factory component utils, and we have just implemented a cover group So note that again, as I pointed out, we are not going to define all the cover groups that are required for the APB. That is not the goal. The goal is to show you overall flavors of how you can implement the coverage at different places. For example, within the APB interface that we were connecting between the DUT and the test bench, we had put an assertion based coverage, and now we are implementing one coverage subscriber within the agent. So we are implementing one cover group called APB cow, and we are just doing the read write very trivial coverage, and we have a transaction, and the main thing over here is this write method implementation, because the subscriber already contains an analysis export and its implementation. And then in the write method implementation, what we do is it will get the transaction that is sent from the monitor that is present within the agent. Okay, this is that monitor which monitors the interface, creates a transaction, sends out, not the protocol checker monitor. So whatever the transaction it has sent becomes available through this write method, and that we are assigning it to our internal transaction handle, and we are calling APB cow.sample, and this cover group is being able to access this particular object because of the scope of being present within the same class. So it's sampling the analysis transaction.we. We are calling an explicit sample method, and based on that particular property value, the bins read or write will get sampled. So this is how you can implement coverage. Subscribers can be instanced within the agent or within the environment as well. So we'll now look into the APB monitor that we had instanced it externally. If you remember, in the TB top, we had instanced the protocol checker monitor. This is meant for holding the concurrent assertions. So this is the interface APB monitor, and it has bunch of these parameters that can be used for customizing this particular protocol monitor. As you know, the interface is also one of the construct that can be actually compiled standalone as well. It has all the equivalent capabilities as module, and we can put anything and everything that mostly what we can put in the module, like we can put always blocks, initial block, you can put concurrent assertion, task functions, anything you can put it within the interface as well. And we are defining all these signals as inputs, okay, because we could have created a mod port as well within the interface and used that, but here we are creating a new interface, different ways of doing things. I'm showing you one of the real example, the way they have done it, and we have these all input ports that are coming in, and then there are two major functionalities that are present within this interface construct. One is the concurrent assertions for the APB bus protocol, and then the you can also implement APB bus functional coverage here as well. So we now have three places, right? The main interface where we are connecting in the coverage monitor that is present within the agent, that is connected to the monitor which is present within the agent, and then this is the external protocol checker monitor which is being built as an interface which is taking all the input ports, because it's not doesn't intend to modify any signals, right? So it's taking all of the signals as inputs, and then you have the bus functional coverage that you can implement it over here. Now let's look at each one of them, like how the assertions would look like, how the bus functional coverage would look like. Again, I am repeating the point that this is not a comprehensive assertion, this is not a comprehensive coverage. It's going to show you few flavors of how you can implement such things, and the main focus is on completing everything and showing you the flavors of everything in order for you to gain end-to-end understanding. Okay, so we'll look at few flavors of assertions that can be put in that interface. We'll start off with some assertions that just do a quick check on the interface signals. So first one is checking that particular signal is in the safe state or is in the correct state. So it's checking that the signal is not unknown. Okay, so this is a property saying signal valid, taking in an argument so that it becomes reusable. Then the sampling event that it is using is at pause edge of clock. It is disabled when the reset gets asserted, and it's checking not of is unknown, whatever the signal parameter that we had passed. and then we are passing P reset in and P cell. These are the key signals that should never become unknown. So that's going to check, and if any one of them X is seen, then this particular property will fail. Note that unless you combine the property with the assert directive, it's not going to become active. So we have done that, and we have given a name. It's important to give the name so that when it fails, you will get to see the name. It makes it easy to debug. And then we have property pcell 1 hot 0. Then similarly, all these properties are being triggered at the passage of our peak clock and disabled when the reset is asserted, and we are using 1 hot 0 of pcell. Okay, so this is interesting. So we are using 1 hot 0 because it means that it can be 0 or 1 bits set. Okay, so because initially pcell could be 0, so and at a later point of time when it becomes operational, only one of them could be set. So it is using 1 hot 0 instead of just the 1 hot. And then we have a bunch of reusable properties to check that after the P cell has been asserted, the signal doesn't become unknown. We know that the signal must hold, right? After the P cell is asserted, that is after the control phase, it must hold, and that we are doing it for P address, P write, and P enable. This is the overlapping. So as soon as the P cell becomes 1 hot, that is one of them has been asserted, from the same clock onwards, it will expect that the signals to not show any unknown values. Okay, and that we are doing it for these 3 control signals. We looked at some individual signal value assertions. So let's look at some of the the signal stability related assertions. So we have one over here which says that after the P cell gets asserted, that both in the setup as well as in the access stage, the signal values should remain stable. So how do we do that? We say not of stable P cell, and 1 hot of P cell is being used as an antecedent, and that gets triggered on this T2, and we use the non-overlapping operator, which means that from T3 onwards, what should happen is that the signal values at T3 and then the T2, because the stable will look at the past, right? So the signal should remain stable and it should not change, and till the point that, and this stability can continue for like *1:$, indicating that you can have it for like multiple wait states. If they come before the access, those gets taken care, and after that 1 clock delay $fell of enable. So then till that point the signal should remain stable, and that has been applied to P cell, P write, P address, and then PW data ANDed with the P write, right? So for all of those signals, we are checking the stability. And next one, we are checking for the fact that once the P enable and P ready are seen together, then the next clock cycle, the P enable must go low, and that is what we are asserting over here. And then we have that once we have like a P cell is changing, then the immediate one non-overlapping clock cycle, the P enable must go high, right? So that is the second clock cycle. Typically in the after the setup stage, in the access stage, the P enable must go high, that we are checking over here. So we looked at a few assertions. Now let's look at the functional coverage that can be implemented in the protocol monitor that's implemented in the interface. So we implemented this cover group. We have set option per instance equal to 1. So if we do create multiple instances of this particular cover group for each of the slaves, then the reporting in the coverage report can be obtained per instance of cover group. We have implemented a bunch of cover points, and then we have implemented a couple of bins. We have done the cross, just a sample cover group. We have instanced this particular cover group for the number of slaves that we intend to implement. created the instance of that particular cover group by doing the new, and then we have declared a sequence which indicates the end of APB transfer, which is the rows of enable and pre-ready. And on this particular sequence, we are using that sequence to sample the cover group. So we are saying cover property, and in the action block we are calling the sample function for the cover groups. For each of the cover group we are calling the sample function, and this is a very important point, that the functional coverage must be sampled at the right place and the right time. So that is very important, and this is the right place and right time because we have put the cover group within the interface where the actual activity is taking place. It's closest, and then it is being sampled at the end of the transfer. So both make sure that the quality of the functional coverage is better. When you do it much more away from the DUT, and then you have the possibility of getting the false coverage, and when you use many sampling events which are not qualified, then also you have the chances of false coverage affecting the quality. So in this case, I think it's being done at the right place and at the right time at the end of the transaction. So this concludes the final part of the series, wherein we looked at the APB protocol from the verification point of view. So we started off from the TB top, and then we dig down further. So at the TB top, we were able to connect the APB interface, pass it through the config DB, and we also instanced an interface based protocol checker at the TB top, which is a module. And then we looked at how the test is able to use the RAL model to generate the read writes, and how we have connected the adapter which translates to APB sequence item. And then we built the environment, and in the environment we were able to acquire the overall environment config that was created by the test to configure the environment. And from that particular environment level config, we extracted the APB agent config, and we passed it on to our APB agent instance through the config DB again. And that particular config DB contained the agent config contained the virtual interface for the APB. And inside our APB agent, we extracted that particular agent config from the config DB, passed that virtual interface to both the monitor as well as to the driver, and we did the various port connections within the agent, our sequence item port, and then the analysis port to port connection, as well as to a functional coverage monitor that was present within the APB agent. So we saw multiple places where we can instance or where we can put in the functional coverage. Then we looked into how the driver drives the APB master interface, how it does the P-cell decoding based on the address range that we had configured within the APB agent config, and how that configurations can be done for the multiple agents. So that aspect also we looked at it, and how it maps to the state machine that we had created. Of course, there are always scope for the improvements, like for example, you can improve it how to do it for back-to-back transfers, right? So that is something that can be improvised within the driver. And then we looked at how the basic monitor has been implemented, which detected various transactions that it's sent it out to both the coverage subscribers as well as to the scoreboard, right? And then we looked at how the functional coverage monitor within the APB agent was implemented, how it was connecting to analysis port, how it was doing the right method implementation within which it was processing the transaction and calling the coverage sample. And then we once we completed looking at this entire structure, which completed the entire hierarchy, right? So the hierarchy was we started from the test, then we went to the environment, we went to the agent. Within the agent, we looked at the driver, looked at the monitor, looked at the coverage monitor within the agent. And once this hierarchy is finished, we came back to the top. At the top, we had the protocol monitor. We went into the protocol monitor, we looked at few assertions, concurrent assertions which check for the value, for the stability of a particular signal values. So how it was able to do that, we looked at few of the examples, and also we looked at how we can implement functional coverage within the external protocol monitor. So this overall concludes how you can do the overall verification environment around your APB protocol. So this concludes the overall series that you looked at the protocol, and then that protocol understanding, you translated it into design, and then you also translated into verification. So I hope this gives you overall perspective of how protocol gets translated to design and verification end to end. And thank you so much for listening. I hope this overall course was insightful, and this helps you. Eventually the goal is, when you look at more complex protocol, it gives you a perspective of how the design is going to happen and how the verification is going to happen, and that is the final real course objective. I hope that this course is able to meet that. So thank you once again for listening. So moving on to few more little involved properties. So this property is checking whether the PW data remains stable. So it waits for the 1 hot of P cell and the P write to start the process. So and the clock edge of T2, we see that the P write and the P cell are asserted, and after that it's ANDing these three sequences. The first one is saying that the PW data should not contain any unknown, and the PW data should remain stable, and then till the P enable goes low, right? So that is till this point the P enable goes low, that is the fell of P enable. And with this star 1 to colon dollar, it is able to control that if there are wait states, it will be able to accommodate them. And because of this AND condition, all of them are expected to start at the same time. So till the P enable goes low, it will expect that the PW data to hold the unknown plus the stable value. And then we have checked that the read data is valid. Similarly, here what we are doing is we are waiting for P enable, not of P write and P ready, and then after that, once the P ready has come, the PR data should remain, should not contain any unknown till the P enable goes low, right? After that, P enable goes low.